Have you ever thought if atoms, the tiny building blocks of everything around us, actually touch each other? It's a question that delves into the heart of quantum mechanics and the nature of matter itself. Today, we're going to explore this intriguing question from several perspectives and solve the mysteries of atomic interactions, atoms, and probability clouds. Firstly, let's define what we mean by touch. In the everyday world, touching means two objects coming into contact with each other, where their boundaries meet. However, at the atomic level, things aren't so straightforward. Atoms don't have hard boundaries. Instead, they exist as fuzzy quantum probability clouds. These clouds are regions where electrons are likely to be found, spread out in wave-like shapes called orbitals. Imagine a cloud in the sky. It has a shape and location, but no clear boundary. Similarly, an atom has regions of high and low density within its cloud. When we say an atom is at point A, we're referring to the high-density region of its probability cloud. This cloud-like nature of atoms means defining touching is more complex than just physical contact. Three possible interpretations. So, let's dive into three possible interpretations of atomic touching. If we consider touching as any form of influence between two atoms, then atoms are always touching. This is because their wave functions, which describe the probability of finding an electron in a particular location, extend infinitely. Even if two atoms are miles apart, their wave functions overlap slightly, implying a minuscule influence on each other. However, this influence is usually so tiny it can be ignored. In practical terms, if two atoms are more than a few nanometers apart, their interactions are overshadowed by those of closer atoms. So, while it's technically true that all atoms are always touching in this sense, it's not particularly meaningful. In the physical world, objects influence each other through four fundamental forces: the electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity. Electrons and protons within an atom are bound together primarily by the electromagnetic force, which also governs the interactions between atoms in molecules and everyday objects. When atoms are far apart, the electromagnetic interaction is weak, but as they get closer, this interaction becomes more significant. For non-reactive atoms that don't form strong chemical bonds, this interaction usually manifests as the van der Waals force. This weak attraction occurs when atoms induce temporary electric dipoles in each other, resulting in a weak electrostatic attraction. Interpretation 2. Significant influence. The second interpretation considers touching as a significant influence between atoms. This typically happens when atoms are close enough to interact electromagnetically in a way that affects their behavior, such as forming a chemical bond. But what constitutes significant? One way to define it is by setting a perimeter around an atom that contains most of its electron cloud, say 95% of the electron probability density. Atoms would then be considered to touch when these perimeters overlap. Another approach is to consider atoms touching when they are close enough to form a chemical bond. For instance, in a hydrogen molecule, H2, the two hydrogen atoms are separated by about 50 picometers and can be considered touching at this distance. In chemistry, this significant interaction is crucial. The entire field revolves around what happens when atoms get close enough to influence each other electromagnetically. Covalent bonds, ionic bonds, and hydrogen bonds are all examples of significant interactions where atoms touch in a meaningful way. Interpretation 3. Exact same location. The third interpretation of touching is the most stringent. Two atoms residing in the exact same location. Under normal conditions, this doesn't happen due to the Pauli exclusion principle, which states that no two electrons can occupy the same quantum states simultaneously. This principle keeps atoms from collapsing into a single point, ensuring that the matter retains its structure. However, Under extreme conditions, such as very low temperatures, certain atoms can be coaxed into the same location, forming a Bose-Einstein condensate. In this state, atoms lose their individual identities and behave as a single quantum entity, effectively touching in a way that defies normal physical laws. So, do atoms ever actually touch each other? The answer is multifaceted and depends on how we define touching. If we mean any influence whatsoever, then yes, atoms are always touching. If we mean a significant influence, then atoms touch when they are close enough to interact meaningfully, such as in chemical bonds. If we mean occupying the exact same space, then atoms never touch under normal conditions, but can under extreme conditions. Thanks for joining us on this journey into the world of atoms and their mysterious interactions. If you found this topic as fascinating as we do, don't forget to like, subscribe to Physics Daily, and hit the bell icon for more deep dives into the wonders of science. Leave your questions and thoughts in the comments below. We'd love to hear what you think.